Well, if embedded systems and IoT edge systems are devices with relatively slower CPUs, less memory, and less storage than desktop PCs, workstations, and servers, then how are embedded systems and IoT edge systems different? When we came out with the first database system created explicitly for embedded systems in 2001, we were mostly concerned with data silos, meaning that the data was captured on the device and never left the device. For example, portable media players need a database system to manage tracks by artist, album, genre, maintain playlists, and so on. The data movement was one way. Once you downloaded the music to your device and the database was built from the MP3 metadata, that was it. The owner had everything they needed to search and play music. Likewise, a television set-top box needed a database to store channel and program information, excuse me, coming from the satellite transponder or the cable head end, but the data movement was one way. Today's set-top boxes are a little more sophisticated, but it's still largely a true statement. You can still find examples of embedded systems as silos, but for the Internet of Things, the story is completely different. The purpose of the Internet of Things is to collect data and make it useful in some way. And part of the reason for the explosion of the Internet of Things is the wonderfully diverse ways that that data can be made useful. Making data useful means it has to be collected, aggregated, shared, and analyzed for some purpose. So enter the modern IoT database system. So whereas embedded systems database systems largely only had to deal with managing data on the device, an IoT edge database system has that and additional challenges to solve. Another evolution in embedded systems to IoT edge systems is the prevalence of multi-core processors. As you know, taking advantage of multiple processing cores doesn't magically happen. It takes effort to write your code to be multi-core aware and not inadvertently cause blocking and serialization of the execution. It requires even more effort to retrofit a large body of code, like a database management system, that was written before multi-core processors became prevalent. To put that in context, Intel released the Core 2 Duo in 2006. So when you're researching your choices for a database management system for your edge device, look into its ability to leverage a multi-core architecture, or at least not hinder your ability to leverage a multi-core architecture. To put a finer point on it, some implementations of the C runtime library for embedded systems toolchains are still rather rudimentary, and a database management system's reliance on the C runtime library can defeat concurrency in a multi-threaded application. For example, relying on malloc and free to manage heap memory. Worse yet, the database system itself can hinder the ability to leverage multiple cores. As a concrete example, the very popular embedded database SQLite uses pessimistic concurrency control, for which the lock granularity is the entire database. So a task that's writing to the database blocks every other task that wants to read or write the database. In this case, a concurrent task that otherwise would be able to execute in parallel with on another core is going to be put into a waiting queue. Embedded systems were largely homogeneous, meaning developers only had to worry about a single target hardware platform. For example, the Apple iPod used an ARM7. Database management systems for embedded systems always had to be able to support different target platforms, or what we call platform independence. Unlike desktop and servers, which are predominantly x86-based, embedded systems could use ARM, MIPS, PowerPC, Coldfire, Easy80, Tile64, and more processors. But the data didn't need to move between systems. So being able to build with different tool chains for different target platforms and operating systems was enough. In other words, the database system code needed to be portable, but the data didn't need to be portable. In contrast, an Internet of Things system is often heterogeneous, not homogeneous. In other words, many different hardware platforms. For example, there might be a Raspberry Pi wearable device, which is ARM32, that connects to a gateway running 64-bit x86 Linux, which in turn connects to cloud servers running Power9 Linux. Now, database system system implementers have a new wrinkle with respect to platform independence, in that we have to be able to move data between architectures with different endianness, different alignment requirements, different word sizes, and so on. So make sure the database system on your shortlist has this covered. One of our customers makes lighting systems for large events like concerts. Sadly, their business has really been hit hard by this pandemic because no one's holding events anymore. But their use case is emblematic of the heterogeneity that I'm talking about. Engineers are generally going to use a PC to develop a lighting program, which of course is an x86 system, which is then distributed to various other devices that could include smartphones, maybe with a Snapdragon processor, tablets, and lighting consoles that might be ARM-based. The program can be updated in real time on any one of these devices and has to be immediately reflected in every other device. Generally, there's going to be about 20 or so such systems that the database has to be distributed to, which in turn is controlling thousands of lighting fixtures. That distributed example is actually a good segue to the next topic, which is connectivity. As I mentioned at the outset, in embedded systems, if there was a need to move data around, it was, for example, for high availability, which also implies that the data was moving between similar systems or like systems, or even identical systems. In other words, they were homogeneous. In addition, we could assume a reliable and a high-speed network. We can't make either assumption with IoT. An IoT system might have battery-powered devices or devices in remote locations and or mobile devices. And that has a couple of implications for database systems. Will the database system support Bluetooth Low Energy, Zigbee, or other communication channels? The next implication is that systems that are battery powered or mobile will have intermittent connections. Database systems cannot assume an always-on connection and will need to have the ability to know what data has been replicated and what data is waiting to be replicated, and a policy for how to manage the circumstance when more data accumulates than the device can hold during a prolonged period of being disconnected. Our solution to this problem is called the Active Replication Fabric. Chris is going to copy these URLs to a chat window for you, so don't worry about scrambling to write them down. The first link is to a web page that describes the Active Replication Fabric. The second link is to a page that describes a demonstration program that we created to showcase the Active Replication Fabric, which you can download and run on your own. Or you can just watch Chris give a demo, which is the third link. Okay, a few words about security. The database on a set-top box, a portable media player, or an industrial environmental chamber didn't really need to be secured. But the database underlying a messaging application on your smartphone, or a video surveillance system, or any number of medical systems certainly do need to be protected. A database system for the Internet of Things should be able to protect the data stored on a device, in other words, data at rest, and ensure the security of the data while it's in transit from edge to gateway, between gateways, and ultimately up to the cloud. That should be another checkbox on your list. The embedded systems examples I've used previously had data structures that fit nicely into a more or less relational database design. For example, the portable music player has artist, album, and track entities where there are one-to-many relationships between artists and albums and between albums and tracks. A conventional row-oriented database system implementation worked really well. In the IoT world, however, we're often managing so-called time series data, which is a sequence of data points, which is usually paired with a timestamp that represents the changes of a thing over time, or the state of a thing over time. The most common example is sensor data. For example, a remote weather station can gather temperature, atmospheric pressure, and wind speed measurements. A smart energy meter might gather kilowatt hours of electricity used at points in time. Time series data is most efficiently stored in a columnar fashion. So whereas the examples I gave before fit nicely into a row-wise organization, time series data fits better into a column-wise organization. Recognize that most database systems, especially row-oriented ones, store data organized much like a spreadsheet. There's database pages that hold rows, and each row consists of some number of columns. A weather station's data might be organized something like this. With this organization, if a client program wants to calculate the average temperature at a weather station for a range of time, the database system has to read entire pages of station IDs, timestamps, temperature, pressure, wind, and wind direction, when all the program is really interested in is the first three entities. Remember, we want to calculate the average temperature, so we really only need the station ID, the timestamp, and the temperature. The I/O processing given this organization for the latter three attributes is just wasted I/O. For this use case, a better way to organize the data is for a database page to contain only values of a single column. In other words, a column-wise organization, and therefore no I/O is wasted. So in this case, we have a row for station ID and its attributes, and hanging off of that row, we have columnar organization for the time series data. Also note that the time series data tends to be highly repetitive and lends itself to a highly efficient compression algorithm known as run length encoding. Very simply, if the value 45 occurs 197 times, it's stored one time with a counter to indicate the number of occurrences. We might only need 8 bytes of storage to represent this versus 197 times 4, or about 788 bytes if we didn't use run length encoding. In our experience, run length encoding typically yields about 90% compression, and that's going to pay big dividends in storage space, I/O, computation, and replication. That superior organization for time series data has resulted in time series databases increasing in popularity with the IoT, dwarfing all the other database system models in the last 2 years. IoT devices have the potential to generate a tremendous amount of highly granular data. Consider a sensor that samples data at 1,000 hertz. That's 86,400,000 elements every day. A device with 10 sensors, each producing a double precision floating point number, would generate nearly 7 gigabytes of data every 24 hours. 7 gigabytes. That's a lot for an embedded system with a slow processor, limited storage, etc. It's entirely likely, though, that for local processing, that granularity is required. For example, in an industrial control system, a controller may need to react instantly to measurement changes. But farther up the IoT ecosystem, it's unlikely that that fine-grained data is actually useful. Ideally, an IoT edge database system will have the ability to aggregate data and replicate only the aggregated data to gateways and servers. It's especially true when the edge device has low bandwidth and or intermittent connectivity. So while the SQL standard aggregate functions can do the basics like average, sum, min, max, etc., more advanced capabilities like window aggregates, grid aggregates, and standard deviation require more advanced analytics. To put a finer point on it, rolling those 1,000 hertz samples up to a grid average of 1 second reduces the data transport and upstream storage requirements by 99%. Most, if not all, large database vendors have recognized the need, or the customer demand, if you will, for in-database machine learning and addressed it in some way. Just go search for SQL Server machine learning or Oracle machine learning, and you'll see what I'm talking about. Examples of machine learning and artificial intelligence are easy to find in the world of big data. For example, a credit scoring agency can combine information regarding an individual's current debt load, their payment history, and other data regarding shopping trends and other behaviors to draw correlations between those behaviors and past credit performance to predict future performance. IoT edge database systems that facilitate machine learning are somewhat more of an emerging technology. Virtually every embedded database vendor that offers an SQL API also offers the usual SQL aggregates, min, max, and the others I mentioned, but that might not be enough. Sorry, you're going to have to search farther to find embedded database systems that support more complex analytical functions that are essential to machine learning, such as correlation, covariance, deviation, and more. Examples of machine learning at the edge are harder to find. But consider an adaptive transmission as one example. An adaptive transmission is one that learns your driving patterns and modifies the transmission's performance accordingly. In other words, the adaptive transmission might delay shifting if it senses high lateral acceleration, or provide for snappy shifting for an aggressive driver, or softer shifting for a more laid-back driver. The arguments for in-database machine learning at the edge are largely the same as machine learning in the enterprise. It's a simpler architecture versus knitting together disparate technologies. That could be particularly important in resource-constrained IoT, edge, or embedded systems, which simply might not have the resources to host a complex tool like Kafka and everything that entails. Or they might simply not be available on the given architecture. In addition, it avoids having to move a lot of data between systems. In other words, you're generating the system on an edge device, but you got to shove it upstream to do this machine learning on it. So if you don't have to shove the data around to do that, it's a more efficient architecture. And as I mentioned previously, edge systems can generate a lot of highly granular data, and it's usually not desirable to replicate such granular data. So the data is downsampled, aggregated, or somehow summarized, but that would compromise the quality of the machine learning. So machine learning at the edge, where you don't have to do that downsampling, can be very useful.